start. We'll start chapter 5 today. All right, can you guys see the PowerPoint?
Yes.
Okay, so today we're going to start chapter 5, another type of bonding model called covalent bond model. This is the chapter guideline, and we're going to cover everything, every topics in this chapter. It's a longer chapter than chapter 4. And before we start, let's take this as a review of chapter 4, and then as a brief introduction of chapter 5 and comparing these two types of bonding. First, ionic bond, we learned in chapter 4, forms between a metal and a non-metal. Again, you can see I put on red. This is the most important piece of message for these two chapters, because after these two chapters, when I give you anything, any compound, you first need to identify, should I apply ionic bond model or a covalent bond model? Is based on this piece of info. Ionic bond forms between a metal and a non-metal, while covalent bond usually from two non-metals or two or more non-metals. Remember when in previous chapter we studied in our periodic table, how do we separate? Where is the line between metal and non-metal? You kind of know when you look at elements, are they metals or non-metals? Number 2, ionic bond in chapter 4, we studied, it is from the transferring of electrons. Transfer of electrons would end up with ions, positively charged ion and negatively charged ions. That's why the ions interact with each other, called ionic bonding. While in this chapter, covalent bonds involves sharing of electrons. The electrons are not transferred from one to another, while two atoms share the electrons between the nucleuses. Number 3, ionic compound do not contain discrete molecules. We said earlier in chapter 4, NaCl, sodium chloride, ionic compound does not have molecules of NaCl floating around in the structure. What we see is a huge network of millions of sodium plus and millions of Cl minus. But one thing we know is for NaCl, the Na sodium plus and Cl minus, the ratio must be 1 to 1. So no matter how many sodium plus you have, you end up with the same Cl minus. But you would never see NaCl molecules in ionic compounds. But in this chapter, we will see that covalent bonded molecules, usually the smallest building block is molecules. Individual molecules, like a person. One person has 2 arms and 2 legs. The same. Compounds we learn in this chapter contains a few number of atoms. They do have discrete molecules. Number 4, ionic compounds are solids at room temperature. All ionic compounds are solids at room temperature. But compounds we learn in this chapter can be in all types of states. Solids, liquid, and gases. Number 5, ionic compounds, their solutions means when you dissolve an ionic compound in water, their aqueous solution, we will learn that in later chapters, usually conduct electricity. Okay, the reason is because of the free ions. We'll learn that in future chapters. But soluble molecular compounds means compounds we learn in this chapter, even though they're soluble in water, they usually do not conduct electricity. Their water solution do not conduct, usually. Okay, there are exceptions. So these are a few comparisons between these two chapters, between compounds of these two chapters, between the model of these two chapters. Again, this serves as a review of chapter 4 and what we're going to learn in chapter 5. So first, let's take a look at what is a covalent bond. Using the simplest molecule, I would say this is the simplest molecule, hydrogen. Hydrogen exists in nature as H2. There's no hydrogen atom floating around. Hydrogen exists, the element of hydrogen exists in nature as H2, diatomic. Why hydrogen exists in nature as H2 is because each hydrogen atom only has one valence electron. And in order for hydrogen to satisfy the octet rule, again, hydrogen, the octet rule is 2. Why? Because the noble gas for high configuration for hydrogen is a helium. Helium only has 2 valence electrons. So in order for hydrogen atoms to satisfy the octet, 2 hydrogen atoms will share a pair of electrons. Share means each hydrogen donates 1 electron. Then the 2 shared electrons holding 2 hydrogen atoms together is called a covalent bond. So you can see there's no really bond. Bond is a concept we invented to better understand the forces. But what is a bond? Bond is basically a force holding molecules, holding atoms together. And what's that force? The force is the shared electron. Guys, can anybody tell me what is the charge for electron? What is the charge for electron?
It's negative.
Negatively charged shared electron pair holding these 2 hydrogen nucleus. What's the charge for nucleus, guys?
Positive.
Positive. The protons are positive. So now you understand what is the basic principle of a covalent bond. It is the same as ionic, basically, charge interaction. The charge of these 2 electrons shared between these 2 nucleus is negative, holding 2 positively charged nucleus together, tight. That's what we call a covalent bond. When you look at a covalent bond, it's nothing but what? Charge interaction. It is the charge of the electrons shared interacting with the charge of the nucleus of these 2 atoms. And this is the simplest covalent bond model. Okay? Now, these 2 shared electrons, again, help each hydrogen atom to achieve a noble gas configuration. The hydrogen noble gas configuration is helium, the first period, hydrogen, helium. So that's an exception for octet. It's not 8, it's 2 for hydrogen. Why? Because the noble gas configuration for hydrogen is 2. So this is how we represent the structure of hydrogen. You can see that 2 electrons, 2 dots shared by 2 hydrogen. And we call that a covalent bond. Here, this page shows you more examples of covalent bond. The first case is hydrogen and fluorine. Guys, if you remember, hydrogen has 1 valence electron while fluorine has 7 valence electrons. Why 7? Because fluorine is in group 7A. The valence number of valence electron equal to the group number, if you guys remember what we learned in chapter 4. So each atom between hydrogen and fluorine donates 1 electron. When hydrogen and fluorine shares 2 electrons, of course, these 2 shared electrons, 1 from hydrogen, 1 from fluorine. Now you can see that hydrogen achieves octet, 2 valence electron. Fluorine also achieves octet, 8 valence electron. Why? Because now fluorine gets the 1 from hydrogen. So via sharing, each one of these 2 atoms achieved octet rule. This is the structure of hydrogen fluoride. You can see everybody satisfy octet rule. If you understand that, There shouldn't be any problems understanding the bottom two cases. Fluorine, F2, and bromine fluoride, BRF. Give you a couple of minutes and please ask questions about the basics of covalent bond model.
What did you call the two fluorides bonded together again?
Fluorine, that's just the element of fluorine, F2.
Okay, thank you.
Fluorine exists in nature as diatomic as well. There's no F floating around. Fluorine exists in nature as F2. Just like hydrogen is H2, oxygen is O2. There's a reason. You can see that fluorine, now you know the reason. Why? Because fluorine atoms need to form a fluorine molecule in order to achieve octet for each one of them. That's why they exist in nature as F2. Okay, some elements exist in nature as monoatomic, some elements as diatomic. Fluorine exists in nature as diatomic. Don't worry about the naming yet. We will study the naming of these compounds in this chapter in detail.
Is there a rule that helps you determine which elements are diatomic in nature and which are monoatomic?
There is. We can talk about that after. If we have time tomorrow recitation, remind me. I'll show you a periodic table. It's not rule. It's just memorized because it's how the work nature works. But it's not hard to memorize. Only a few elements exist as diatomic, most as monoatomic. Any other questions, guys? All right, next. Now, because we call shared electrons, a pair of electrons, a covalent bond, so we use a dash to represent that bond. So as you can see here, in these cases, these are the same as what we have shown so far. This is this here. We use a dash to represent the shared pair of electrons. Again, a dash represents a shared pair of electrons. That means two electrons. And we call that, again, a covalent bond. So what does this dash mean? This dash means two dots shared. And of course, the others electrons that are not shared like these, we don't use dash. They're still dots. But the shared pair of electrons, because we call that a covalent bond, we use a dash to represent, to discriminate the ones shared that's versus the ones that are not shared. Don't worry, we'll talk about right away. How do we call those ones that are not shared? Here, this picture shows you, again, the bonding electrons, the shared pair, we use a dash to represent them. But the ones that are not shared, they have their own names. And sometimes they're very important. We'll talk about in this chapter as well. These electrons that are not shared are called non-bonding electrons or lone pair electrons or lone electron pairs. I always call them lone pair electrons, lone electron pairs, no matter what. I use the second, but you will see both names. The ones that are not shared electrons are called non-bonding electrons or lone pair electrons. A lone pair means these electrons, in most cases, they come in pairs. Why? Because octet rule has 8 valence electrons. There's no 7, there's no 5. So that's why they're always in pair, even numbered. There are odd numbered species. We may talk a few in this chapter, but they're not common. So this is how do we represent a structure of a molecule using elements symbol and electrons. And remember, we replace the shared electron using a what? Using a dash. Okay, using a dash. This picture shows you more examples. More examples means 3 molecules. Oxygen with 2 hydrogen, nitrogen with 3 hydrogens, carbon with 4 hydrogens. I'll give you a few minutes to see if you understand these three examples, especially the structure of each. For example, I'll explain the first one. You understand this, the second one and third one. One oxygen atom need two hydrogen atoms to make a molecule. Why? Because oxygen is group 6A element. It has 6 valence electrons. If it is a 6 valence electron, means what? Means it needs 2 more to satisfy the octet rule. So 2 hydrogens, 1 hydrogen has 1 electron. So 2 hydrogens, each hydrogen donates 1 electron to share with the oxygen. Then you can see everybody is satisfied. Hydrogen 2 valence electron, oxygen 8 valence electrons. And we replace the shared electron using a dash. So we have 2 OH covalent bond and 2 lone pairs on the oxygen. Total is 8. Again, each bond is 2 electrons. So 2 bonds and 2 lone pairs, total is 8. This is the structure of water. Okay, this is the structure of water, H2O. With that logic, guys, take a look at the second molecule and the third molecule, NH3 and CH4. Give you a couple minutes. Please ask me questions. Guys, please feel free to ask questions, okay?
On the
Yes.
last two, why did you name the H last?
Name the H, what do you mean?
You said NH3 and CH4, I thought.
Yes, not name, I mean, when the formula writes the formula, it's NH3 and CH4, yes.
Why is that?
That's a good question. I don't really know. I can check for you. That's how it's kind of like a I mean, I shouldn't say it. It's kind of like a tradition for me. I never thought about that. Like NH3 is NH3. Nobody called it H3N, or just like CH4, nobody called it H3. I can check that for you. Why water is H2O, not OH2? I can check that. Good question. I never thought of it because it's, for me, it's kind of like, that is it. That's how we say the molecule. NH3 is ammonia, CH4 is methane. I'll check that for you. Good question. Why we put C in first. There must be some grammar thing. I've never thought about it because this has been like home. Your life, whole my life knows, okay, NH3, CH4, and H2O. Never thought about why hydrogen is found. Good question. I'll check that for you. Okay, this is ammonia. You guys have bought ammonia or you have seen ammonia grocery store. Ammonia smells bad. And this is CH4, natural gas. The one, if you have natural gas in your house, this is the one you're burning, CH4, kind of methane. Any questions about the structure though? Again, I'll check, thank you. I'll check that for you. There must be some grammar thing about these trivial things, but good question.
What is the third structure showed listed? The one with the all dashes. Is that the same thing as Lewis structure, or does it become something else when it's only dashes?
Because there are four pairs of electrons are all shared. You can see that carbon has 4 valence electrons. So each carbon needs 4 hydrogen to share, because you need 8 total. Carbon only has 4. So that means these 4 pairs around carbon are all shared ones. Remember, we said shared one we replace with a dash. That's why carbon has 4 dashes. And also means carbon has no lone pairs. Why? Because 8 electrons are all shared between carbon and hydrogen. Does it make sense? That's why you only see dashes, no dots.
Okay.
Yes, 4 pairs, 4 dashes means 80 electrons. If you have 80 electrons, that's enough because octet. Right. Carbon has no lone pair electrons or no non-bonding electrons. All electrons are bonded, are bonds. Okay. Sometimes atoms share more than one pairs of electrons. So covalent bonds comes in usually 3 types. If one pair of electrons is shared, like we have seen all these cases with a single dash, we call those bonds a single covalent bond, means 2 electrons shared. But sometimes atoms will share 2 pairs or 3 pairs of electrons. If that's the case, we use a double dash or triple dash to represent 2 pairs or 3 pairs respectively. And we call those bonds a double covalent bond or a triple covalent bond, shortly double bond or triple bond. We will talk about the Lewis structure of this guy in the future, but I do want to use this one example to show you why nitrogen also exists in nature as N2. Nitrogen is a group 5 element. It has 5 valence electrons. 5 valence electrons means it needs 3 more to satisfy the octet rule. So each nitrogen gives 3 to share. Each nitrogen gives 3 to share means what? There's 6 electrons shared. 6 electrons, 3 pairs. That's why between 2 nitrogen atoms, there is a triple covalent bond. But if you look at the structure, triple covalent bonds means what? 6 electrons. And each nitrogen also has a lone pair, non-bonded. So everybody gets satisfied. 8, 6 plus 2, 6 plus 2. That's why nitrogen exists in nature as N2. And nitrogen is very stable because of the triple bond. Nitrogen is basically for us. We breathe nitrogen in, we breathe nitrogen out. And nitrogen is rarely used by plants either. Only nitrogen is used by some microorganisms, some bacteria. Why? Because nitrogen, the bond is too strong. So this picture, again, don't worry about the CO2. We'll talk about the Lewis structure in the future. This picture I want to show you. When we talk about covalent bond, there are 3 types. Of course, most covalent bond you see will be a single covalent bond, but atoms sometimes do share with each other 2 pairs or even 3 pairs. So we will see double covalent bond or triple covalent bond. Not uncommon, but we do see them, but not as common as single bond. Okay, not as common as single bond.
Are double or triple covalent bonds stronger than a single bond?
Yes, double bond is more stronger than single bond because it's more shared. Remember, covalent bond is all about charge. Double means 4 electrons holding nucleus together. Triple bond means 6 electrons holding nucleus together. Of course, charge interaction is stronger, bond is stronger. We'll talk about bond length when we see this topic, but yes, double bond is stronger than single bond. Triple bond is stronger than double bond. Okay, before we discuss how do we show the Lewis structure? Don't worry, you guys have seen a lot of molecules. You may be, oh, wait a minute, there's so many molecules. How do we represent, how do we tell the people how many electrons they share? Don't worry, we have a method of drawing structures in this whole chapter. That's one of the most important topics. But I do want to introduce you a very unique type of covalent bond. Usually, like we studied all these past 25 minutes, covalent bond is formed between 2 atoms. Each atom donates a single electron to share, like this top case. Atom X donates 1 electron, atoms Y donates electron, then they share a pair of electrons. That's what we call covalent bond. This is what we have learned so far. That's the most commonly seen type of covalent bond. But sometimes covalent bond is also formed in this case, in this format, in which the shared electron pair come from 1 atom only, not 1 from each. You can see that in this case, for example, X-rays still share a pair of electrons in the end, but these 2 shared electrons came from X only. Y doesn't bring anything to share. But in the end, they're still sharing the whole pair. You're still making a covalent bond, but that electrons shared came from one atom only. The other one just providing some empty room to share. And we call that type of covalent bond coordinate covalent bond. Coordinate covalent bond. And that type of covalent bond is not the most common one, but there are many cases you will see a coordinated covalent bond. One example I want to give you first is NH4 plus. Guys, you learned chapter 4. Anybody remembers the name of NH4 plus? What is this? Anybody remember? We learned chapter 4 of this guy. What is the name of NH4 plus?
I'm looking at the chart, but it's ammonium.
Ammonium. Okay, ammonium ion is NH4 plus. So I want to show you how does NH4 plus is formed. How is it formed? If you guys remember this chart, when nitrogen makes a molecule with hydrogen, we end up with not NH4, but NH3 plus. I'm sorry, NH3, not NH3 plus. Take a look. This is NH3. Now let me draw the structure of NH3 here. N, H, 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 and there's a pair of lone pair electron. This is NH3. Nitrogen satisfy octet rule, 8 valence electron around it. You can see that it's 8. 2, 2, 2, and 2. Now, if there is a hydrogen plus comes close. What is hydrogen plus? Hydrogen has 1 electron. If hydrogen loses 1 electron, hydrogen becomes hydrogen plus. This is hydrogen plus. And we call it a proton. If you guys remember, hydrogen has only 1 proton, 1 electron. If that electron is lost, what's left behind is what? A proton. That's why we call hydrogen plus a proton. Now, when a hydrogen plus comes in, we know hydrogen plus has no electron because hydrogen has 1 electron. Again, hydrogen plus means the electron is gone. So hydrogen is empty, has nothing. But if you notice that nitrogen, this guy has 2 electrons to share. So when N and H plus make a new bond, this bond is what we have been saying a coordinated covalent bond. Because nitrogen can donate these 2 electrons to make a new bond with the incoming hydrogen plus. So we end up with this guy, NH4 plus. Okay, NH4 plus. This is a new bond. If you want to ask, I mean, there's no way we can tell which one new bond anymore after the molecule is made, by the way. But you can assume this is a new bond. What's that new bond? 2 electrons. But those 2 electrons come from where? From nitrogen himself. The hydrogen plus doesn't give anything. Hydrogen plus is empty, has no electrons. So this shared pair of electrons actually came from nitrogen himself. And this is a coordinated covalent bond. But like I said, after the coordinated covalent bond is formed, you will never tell the difference of these 4. You can see they're all NH4, NH, NH, NH. They're all the same now. They're all covalent bond. There's no way we can tell which one was the coordinated one. Nobody can tell. They're all the same now. Coordinated covalent bond only exists when you understand the forming process. But once the bond is formed, these 4 NH bonds are the same. NH bond. What is an NH bond? 2 electrons shared between N and H. And this is the structure of an NH4 plus. You guys all wonder what the heck is polyatomic ion. This is NH4. This is what NH4 looks like. N with covalent bond with 4 hydrogens. And nitrogen still satisfy octet rule because you can see 8 valence electrons. And the whole thing bears a positive charge. Okay, you can see I put a positive charge outside the bracket. Why? Because the charge belongs to the whole thing. Okay, belongs to the whole thing. Does it make sense, everyone, about coordinated covalent bond?
Yes.
I will ask you questions in your quiz. I remember that in chapter 5, of course. Ask you to recognize a coordinated covalent bond. You only need to recognize them. If I give you a molecule, you can see it does the molecule has coordinated covalent bond. Okay, this is another example I want to show you. In HOCl, this molecule, this is HOCl, what it looks like. Every bond is, all covalent bonds are ordinary covalent bond. There's no coordinate. But this molecule can make a new bond with an oxygen if we have an oxygen coming in. How many valence electrons for oxygen? 6. 6 means what? This oxygen needs 2 electrons to satisfy octet rule. So these 2 electrons can be used to form a new bond with the incoming oxygen. If you guys take a look, the oxygen has 6. It cannot give anybody to share. Oxygen needs 2 more. So the oxygen cannot provide the empty room. But the chlorine has lone pairs that are not used for bonding yet. So chlorine and the oxygen, these 2 guys can make a new bond. Using what? Using the electrons from the chlorine himself. And that's the new bond we're talking about here. I'm putting the arrow here. Now take a look at this new bond. This new bond has 2 electrons in it. These 2 electrons came from where? From chlorine only, not from 1 to each from each. And that bond is called a coordinate covalent bond as well. But once the coordinated covalent bond is formed, again, there's no way we can distinguish one from another. It's just a covalent bond, 2 electrons. Okay, 2 electrons.
So how do you identify a coordinate covalent bond?
Good question. Normally, if you see a bonding electron like this, if you see a case like this, if you look at a bond, if the number of electrons missing from a atom equal to the number of electrons in the bond, that means the electrons in the bond came from one atom instead of another. Usually it's 1 from each, but if you look at this bond, oxygen has 6 valence electrons. So that means this oxygen doesn't even have any electron donated. Take a look. This oxygen, originally this oxygen has 6 valence electron. After the bond is made, the 6 electron is still here. Do you guys see that? Let me erase it. Clear pin marks. Oxygen, again, has 6 valence electron. After you make a bond, this oxygen, those 6 electrons are not used for bonding at all. Do you see that? Means what? Means the bond between the Cl and O these 2 electrons doesn't even come from oxygen. If it doesn't come from oxygen, it means come from somebody else. And that bond is a coordinated covalent bond. That's how you recognize it. Just ask yourself, originally, how many valence electrons does it have? If any of those valence electrons are used for bonding, if they're used for bonding, that means it's not coordinated because you donated 1 from each. But if this oxygen doesn't give any electrons for bonding, it still has those 6 by himself. That's called the lone pair. That means none of those 6 electrons were used for bonding. Means what? Means the bond came from the other guy. Does it make sense?
Yes, I think so.
Okay, so that's how you recognize a coordinated covalent bond. Okay, how you recognize a coordinated covalent bond. Any questions, guys? Again, you will see examples in your book. Practice, and I will ask you questions in your quiz and tests. Ask you to recognize. If I give you a few molecules, give you structures, you need to tell me which one of the molecules or which molecule contains coordinated covalent bond, or I just simply ask you right or wrong. This molecule contains coordinated covalent bond, yes or no? Yes or no. All right. I think there are practice in your book after the chapter. Next comes the most important topic in chapter 5 is how do we draw a Lewis structure? Again, guys, if you cannot draw a Lewis structure, then you're done for this chapter. There's no way you can do the rest of the chapter because everything else on this chapter is based on a Lewis structure. Because remember, we're looking at molecules now. It's no longer a huge network. Molecule is like a person, tiny person has a few atoms in it. We need to show people what the person looks like. We need to show people the structure of the molecule. And that structure is called a Lewis structure. So here are the steps. Again, I guarantee you, I never ask you to memorize these steps. You don't need to tell me the steps. I only need you to follow the steps a few times using the guide, then throw the steps away and draw Lewis structure in a very, very, very master way. Okay, guys, I cannot say enough. Lewis structure is the prerequisite for this chapter. Without the Lewis structure, you cannot do anything else from now on. Okay, step 1, calculate the total number of valence electrons in a molecule. Okay, you can read the whole sentence. I want to do a summarized version for you. Step 1, calculate the total number of valence electrons in a molecule. Why we only care valence? Because only the valence electron used for bonding. We talked about in chapter 4 already. Chemistry is the chemistry of valence electrons. So if I use a molecule SO2 as an example to show you guys the steps, can anybody tell me the total number of valence electron for SO2? Let me ask somebody. Caroline, can you tell me the total number of valence electrons in SO2?
Is it 12?
Where did you get the 12?
Sulfur has 6 and oxygen has 6.
Very good so far. But how many oxygen do you see there?
2.
2 oxygen. So total is
24. 18, I'm sorry.
okay. Your math teacher is gonna hate you. 18. 18. Sulfur has 6, you're right. Oxygen has 6, you're right, but we have 2 oxygen. Remember, like I told you, it's like a person. One person has 2 arms. This guy has 2 oxygen. You have to count both oxygen. So total 18 valence electrons. Very good. Except the math teacher part. 18 valence electrons. Step 1 done. Step 2, write the molecule in a way so that atoms are bonded to one to another using a single covalent bond. But you have to determine which one of these atoms is the central atom. If I use my own word to translate step 2 is basically you need to draw the skeletal of a molecule. The skeletal molecule can be completed by first determining the central atom, which is usually the one appears only once in the formula. In this molecule SO2, which one appears only once? Sulfur. If that's the central atom, then the 2 oxygen will be the surrounding ones. And we bond the central atom and the surrounding ones with a single covalent bond. And this is called the skeletal of the molecule. This is basically what step 2 asks you to do. Again, guys, skeletal of the molecule, just show people how atoms are bonded to each other. Remember, we're talking about molecule. You have your body bonded with your 2 hands, 2 arms. The same way, you have a central atom bonded with a few surrounding. And usually the one which appears only once in the formula will be the central atom. There are exceptions, but I will tell you the exceptions if there is exception. And after you determine the central and the surrounding ones, you bond the central and the surrounding ones with a single covalent bond. Javius, a single covalent bond means what? What is a single covalent bond?
It's just transferring one.
What is a single covalent bond? What is in that dash? What that dash mean?
That is transferring one of the valence electrons.
No. Anybody can tell me what does the bond mean? A bond means what? What does the bond mean? Anybody?
Two atoms share one pair of electrons.
Two electrons. Two atoms share a pair of electrons. A bond means what? Two electrons. Okay, a bond means two electrons. So now I use two bonds, means I used 4 electrons. I need to subtract 4 from 18. Total is 18. Remember, guys, we did previously, total is 18. Now you use the 4. Here, you use the 4. You only have 14 left. Still with me, guys? Everyone? Still with me?
I'm not entirely sure.
Which part? Which part?
How do we lose 4 of the valence electrons?
Because you
does it-
use 2 to make the bond. The bond contains 2 electrons. You have 2 bonds now. In the structure, you use these 2 bonds. The bonds are from valence electron. Remember, we only play with the valence electron. Total is 18. You draw 2 bonds in the skeletal. That means you used 4 electrons to make those 2 bonds. Each bond is 2 electrons.
So then only 14 are available.
Correct. It's correct. You subtract 4 from the total. That means in the future, you only have 14 to put in the molecule. Remember, we're doing we want to, by the end of it, complete the Lewis structure. The Lewis structure means what? Atoms and bonds and electrons. So now you can only use 14 now because you used 4 already. I guess I should say that. Yes. Does it make sense now, guys? You have 18 total to play with, to add into the structure. Now, after we provide the skeletal, I used 2. I used 4, I'm sorry, 2 bonds. Then you only have 14 left to add in. Okay?
For clarity, could you go ahead and put the dots on the oxygen
Not
and
yet.
sulfur?
This is step 2. This is step 2. We're not there yet. Again, guys, follow these steps. Otherwise, you will definitely make mistake. Follow the steps, step by step. Don't over to other steps. So far, we only connect the central with the surrounding with a single bond, and then subtract the number of electrons used in that single bond from the total. Total is 18. I subtract 4 from 18. I have 14 left. Good?
Yes.
I have a question.
Yes.
If it's a single bond, why are 2 electrons involved? That's confusing me.
Single bond is 2 electrons. That's what we have been talking, right? Take a look. A bond means 2 electrons shared. This is a bond here. See that?
Okay. Yeah, that makes sense.
This is a bond. I put 2 dots here. This is a bond. A bond means 2 electrons.
So they're giving each other one of their electrons, and that makes it 2.
For that case, yes.
Okay.
For that case, those 2 electrons come from one from it. I mean, these 2 electrons came from one each from each hydrogen. In that case, in this case.
Okay.
Yes. Next, adding non-bonding electron pairs about the outer electron first to satisfy the octet rule. Outer electron means what? The surrounding ones. So when you add the dots to the structure, you start with where? This is very, very important, guys. This is what we had before. Now, you add dots to the structure, but adding the dots pairs to the surrounding one first. Or if I want to say this step in my language is satisfy the octet rule from outside in. You start with outside first. So tell me, guys, oxygen, the outside ones, how many electrons do I need to put to satisfy octet rule?
Oxygen will need 2.
Oxygen, how many electrons do I need to put on this oxygen? Look at the structure. How many electrons do I need to put on this oxygen to satisfy the octet?
Bonded with 1, so it would need another one, an additional 1.
What is
This is the
octet?
part that's confusing me.
What is the octet? What does octet mean?
It needs to have a total of 8 valence electrons.
How many does oxygen have now? Look at the structure. How many electrons does oxygen have? Now, look at the structure I put on here. The oxygen bonded with sulfur. How many electrons does it have now?
It only has 2.
Only has 2 because
You
it's
need
1
6
bond.
more.
So you need 6 of it. Very good. Does it make sense? Every oxygen needs 6 more to satisfy the octet rule. Does it make sense, guys? Everyone?
Yes.
I think so.
Now, 6 here, 6 there. We used 12. So how many left? 14 total now. Use 12 to satisfy the octet for these 2 oxygen. How many left? 2 left. 14 minus 12 equals 2 left. And step 4, I put the remaining 2 on sulfur. Again, from outside in. So this is what we end up with after step 4. Questions, guys? Questions? Okay, let me ask you a question. Look at the structure here. I put in the rectangle. Do you see 18 electrons here? We have total 18. Remember, we started with 18. Do you see 18 electrons here? Guys, do you see 18 electrons here?
There are 14 lone electron, well, 14 lone electrons in lone pairs, and then there are 2 bonds.
So
Which
do you see
each have-
18?
Yes.
Yes, there are 18 electrons. Very good. So keep checking. You are not using more than 18 or less than 18. By now, you should use all of it. Question number 2. Is everybody happy? Happy means, is everybody satisfied with the octet rule?
Doesn't sulfur still need 2 more electrons?
Very good. Sulfur is not happy. We satisfy from outside in, means oxygen is happy. No problem, because we start with oxygen. But sulfur, we simply place the 2 left. We didn't ask if sulfur is happy or not. So if you look at sulfur, sulfur is not happy. Sulfur still needs how many? 2. But we don't have any more. We used 18. So keep those in mind. The question I'm asking you, we have 18 used all, nothing left. You cannot put 2 more on sulfur. But sulfur is still not happy. In that case, we borrow 2 from the oxygen, changing the non-bonding to bonding. So we end up with a double bond with oxygen. This is the final structure. Okay, let's turn me back and forth. Take a look. I borrowed 2 electrons from oxygen, but I'm not taking it away. I'm just changing the bonding to non-bonding. So what happens here? Let me do it over here too. I'm changing these 2 non-bonding to bonding. I'm not taking it away. These 2 still belong to oxygen, but now instead of belong to oxygen itself, now it belongs to what? Shared. So we create a double bond. Now, do you see sulfur happy, guys? You guys see
Yes.
sulfur happy? Copper is happy. Everybody's happy. Now we still have 18 here if you count. Don't add more or less. You still can have 18 here, but now everybody's happy. And that's the correct Lewis structure. This is what it means for step 5. If the central atom is not happy, try multiple bonds. Simply borrow the one from non-bonding to bonding. These are the steps. Again, guys, if you follow all the steps, step by step, you will never get it wrong. But if you jump around, if you don't follow the steps, you cannot get a correct Lewis structure. Do not have your own way. This is the way. Okay, I don't recommend any other ways. This is the way until you get very comfortable in the end. This is the way. Okay? Let me try you with another example to show you these steps using SO2. I'm sorry, CO2. Guys, step 1, using CO2. I'm practicing with CO2. Can you tell me the steps? You read for me the steps. Step 1. Anybody? CO2, step 1.
We need to calculate the total number of valence electrons available.
How many? How many? For CO2. How many?
It 16?
16, very good. Carbon has 4, oxygen has 6. You have 2 oxygen, so 4 plus 6 times 2, 14, 16. Total 16, very good. Step 2. Step 2, do what? Anyone? Draw the what?
The chemical symbol of the atom with the central atom in the middle.
Central atom in the middle, we have surrounding. And then what? Bond the central with the surrounding with a single bond. Right? After we bond it, we need to subtract how many? Everyone, subtract how many?
We used 4.
Yes, we used 4, 2 bonds. So we subtract 4 from the total. We have 12 left. So far good, everyone? We call step 2 the skeletal of the molecule. This is the skeletal. Carbon is the central, oxygens are surrounding. I'm bonding the central with the surrounding with a single bond. A single bond means 2 electrons. I used 4. So we have 2 left to play with. Step 3, guys. Come on, I want you to kind of going with me the steps.
So in your words,
Say something.
Satisfy the octet rule from the outside in.
Very good. You can just use my words. Like I said, you never need to memorize these steps. You only need to use the steps to correct the structure. Satisfy the octet from outside in. So tell me, how many electrons do I need to put on oxygen from outside to satisfy them?
You need to put 6 on each oxygen.
6 on each. Very good. 1, 2, 3, 4, 5, 6. Okay, let me join the dots nicer. 1, 2, 3, 4, 5, 6. Okay. 6 on each means what? 12. Minus 12. I have 0 left. So that means what? I have 0 to put on the carbon. I'm done. I cannot put any electrons anymore. Now I need to check carbon. I satisfy oxygen from outside. I'm done. I don't need to worry about oxygen. Oxygen is satisfied. But carbon, I need to ask, how many electrons is carbon missing for the octet?
4.
4 means what? I need to borrow 2 from the oxygen, borrow 2 from the oxygen. So the Lewis structure is this. Everybody happy? I mean, everybody, I mean COO. Is everybody happy with 8? And we still have 16 electrons. So you check 2 things. Is everybody happy? Number 2, do we use a 16? Do you see 16 electrons in there? If you're good, your structure is correct. Questions? It's your turn, guys. Ask me questions.
I think it makes sense to me now.
Thank you. Guys, like I said, you guys might be shy and I don't know, but this topic is the most important one in this chapter. Not only you will see millions of questions in your testing quizzes for Lewis structure, because you will use this for the rest of the whole chapter. The first job is to provide a correct structure before you can answer any other questions based on the molecule. So please understand the steps of drawing Lewis structures. Okay, I have one more example for you before we move on. Let's try the third one using SO4 2 minus as an example. Anybody remember what is SO4 2 minus? SO4 2 minus, anybody remember? We're learning chapter 4 as well. What is it? All right, yeah, I'm tired of asking. You guys don't have response. SO4 2 minus is called sulfate. Okay, sulfate. It's a polyatomic ion. So let's draw the Lewis structure of SO4 2 minus. Of course, drawing Lewis structure, first step is count the total number of valence electrons. Anybody can tell me how many total number of valence electrons in SO4 2 minus?
30.
30? Anybody agrees or disagrees?
I agree.
You agree? 30? Anybody else agrees? Unfortunately, 30 is not the correct answer. SO4, sulfur has 6, oxygen has 6. So total is 30. You have 5 of them. Sulfur is 6, oxygen is 6. So total is 30. But why I say 30 is not the correct answer is because you guys said 30, forgot about the charge. The charge is what? 2 minus. 2 minus means what? You have 2 negative charge on this guy. Where does those 2 negative charge come from? From 2 electrons. This thing is not neutral. Means the SO4 has 2 extra electron gained on top of the total valence electrons. Because the charge again is -2. Each electron charge is -1. This guy is not a molecule, it's an ion. What is an ion? Ion means the atoms gained electrons. That makes it an ion. How many electrons did it gain? 2 electrons gained. So instead of 30, the total is 32. Does it make sense for both of you who said 30?
Yes.
Okay, very good. This is the first time we see this. That's fine. You make a mistake, you remember even better. When you see an ion, look at the charge. If you see negative charge, add on top. If you see positive charge, means what? You need to lose, you need to get rid of some electrons. Depends on what the ion is. So SO4 2 minus sulfate has 32 total. Step 2, draw the skeleton of the molecule. Central atom, obviously what? Sulfur. The surrounding is oxygen. Easy. Sulfur surrounding by oxygen. I'm connecting sulfur with oxygen with single bond. After I use single bonds, how many electrons do I have left? How many electrons do I have left? Total
20.
valence. Where?
24.
I'm sorry?
24.
Very good, 24. 32 minus 8, 24 left. Next step, satisfy the octet rule from where? Outside in. Oxygen, again, needs how many to satisfy?
6.
6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. How many do I have left?
None.
0.
None, 0. Very good. So I satisfy the oxygen. I have none left. I check sulfur. Is sulfur happy?
No.
No. How many does it need then? If it is not happy, how many does it need?
8. Oh,
8. Does sulfur have 8? Yes, sulfur has 8 already. 4 bonds, 8. So sulfur has 8. Sulfur is happy in this case. And we don't need more electron. We have 0 left. So this is the correct Lewis structure for sulfate. See, everybody's happy. We have 32 total. Now you have an even better idea what a polyatomic ion look like. This is a polyatomic ion. What is a polyatomic ion? It's a very big entity, but the atoms in the ion are bonded through what? Covalent bond. You can see they're bonded to it. The whole thing has a charge. It's an ion, but the S and O's are bonded through covalent bonding. So compounds containing polyatomic ion are examples of compounds containing both ionic bond and covalent bond. Here's the example, K2SO4. Why K2? Because potassium charge is +1, SO4 charge is -2. You need 2 potassium to make the total charge 0. This compound is an ionic compound. Why? Because you have a metal and a polyatomic ion. Metal is potassium plus polyatomic ion is sulfate. So this is an ionic compound. But what makes this ionic compound special is this ionic compound contains not only ionic bond, but also what? Covalent bond. Where is the covalent bond located? In SO4. In SO4, S and O4s are bonded through covalent bonds. So if I ask you, what is a can you give me an example of a compound containing both ionic and covalent bonds? You use what? You use these compounds. What compounds? Ionic compounds containing polyatomic ions. Carbonate, sulfate, ammonia, phosphate. These are compounds containing ionic bonds and covalent bond. Again, where is the covalent bond located? In the structure of these polyatomic ions. SO4, we use an example. So guys, I have practiced with you 3 times. Like I said, I will never ask you what is step 1, what is step 2. I will ask you a Lewis structure. Any questions? Or you want me to practice again? If you want to practice me, you give me a molecule. Guys, any questions regarding the most important topic of this chapter, drawing Lewis structure?
I have a question about the structure right in front of you.
Mm-hmm.
The sulfur has 8 bonds, but doesn't it
4 bonds.
I meant 8 electrons.
Right.
But wait, okay, I think it made whatever was going on in my mind. I think I understand now. Never mind.
Yeah, 4 bonds is 8 electrons. Each bond is 2. Okay, that's why we started very early, introduce what is a bond. A bond is 2 electrons. Okay, the reason we put a dash is we want to distinguish the ones in a bond, means between atoms, versus the one that's not shared. That's why we use dots. We call them lone pair or what? Non-bonding. These are all lone pairs. But the dash is the one shared, not lone. They're shared. Any other questions, guys, about how to draw a correct Lewis structure for molecules and for ions, for polyatomic ions? Okay, Yes,
I was going to say with this structure, you still have the -2 on the outside. Is
correct.
all of the elements are satisfied. They have the right number of valence electrons, they have the right number of bonds. Do you still leave that 2 negative there so that it shows that it
Yes.
can bond with something positive?
Yeah, this is an ion, means you need, they are used to make ionic bond with some other positive ions. Yes.
Okay, thank you.
Remember, SO4, you guys did before, only contains how many valence? 30. But this guy has 32, means what? It need carry 2 negative charge because you have more than two more electrons than protons. Okay, you have 2 more, this guy gained 2 more electrons. That's why you have 32 instead of 30. Okay, the charge from the extra 2 electrons.
Okay, that makes sense. Thank you.
Yes. All right, next. Okay, I'll give you a brief introduction here, and then I'll let you go for today. One of the next tasks when we study a molecule is, after we know the Lewis structure, we wanted to know what is the molecule, or what does the molecule really look like? Because when we draw Lewis structure, no matter how you draw it, it's either on a screen or on a piece of paper. There are 2-dimensional backgrounds, a paper or my screen. But molecules are not necessarily 2-dimensional. Molecules are 3-dimensional entities, objects. So based on the Lewis structure, we first want to know is what the molecules really look like in a 3-dimensional way. And we call that the geometry of the molecule. Again, you draw the structure on paper. It doesn't show what the molecule really look like. They just show how atoms are bonded to each other. But we want to know next is the geometry of the molecule, because the geometry will tell us further physical and chemical property of a substance. That's why, guys, I said everything starts with the Lewis structure. You have to do the Lewis structure first. Now, how do we know the geometry based on Lewis structure? We use a theory called VSEPR, valence shell electron repulsion, electron pair repulsion theory. Don't worry, you don't even need to know that name. You can call it VSEPR or V something's theory, it's fine, as long as you understand what the theory is. The theory is based on the structure around the central atom. On the central atom, if you take a look at the structure we have drawn before, this one here, this is this Lewis structure for SO2, here, Lewis structure for SO2, this is central atom, this is Lewis structure for CO2, this is Lewis structure for that guy, no matter which one. On the central atom, there are always groups of electrons. The groups of electrons can either be bonded or non-bonded. Again, I'm looking at examples that we did before. Take a look. The central atom, on the sulfur, the central atom, we have a single bond. We have a double bond. We have a what? A lone pair electron. So this sulfur actually has 3 groups of electrons. Group means electrons are placed together. This carbon, this CO2, what's the central atom? Carbon. On the carbon, there is a double bond on the left. There's a double bond on the right. So on the carbon, there's no lone pairs. We have 2 groups of electrons. This sulfur, we have 4 single bonds on it, no lone pairs. So this sulfur, the central atom actually had 4 groups of electrons. No matter how many groups of electrons, the theory is based on these groups of electrons will try to minimize their repulsion. How do they minimize their repulsion? Because they're all electron groups, no matter bonding or non-bonding, because they're electrons. Electrons are both negatively charged. So they will repel each other. If they repel each other, the best geometry will be what? Their repulsion is minimized. How do they minimize that? As far away as possible away from each other. If they're further, the repulsion is smaller because they're like magnets of the same type. So the theory is based on minimize the repulsion of the central atom electron groups, or you could say maximum distance of these electron groups. Maximum distance of these electron groups. Now, before we start, let's summarize how do we count the number of electron groups on the central atom. Again, guys, when we determine the geometry of a molecule, we only care what? The central atom. The central atom will determine the geometry. Think about it. When you look at a flower, what determines the shape of a flower? The center of the flower. The petals depends on the center. You can have 3 petals, you have 5 petals, but the center determines the shape or geometry of a flower. The same idea. When we talk about molecule, the central atom determines the shape of the molecule, of the geometry of the molecule. So we'll talk about how to determine the shape. Let's take a look. How do we count the number of electron groups on the central atom? Very easy. Number 1, no matter you're looking at a double bond or triple bond or a single bond, as long as we're looking at a covalent bond, they all count as one electron group. A single bond is one group. A double bond is one group. A triple bond is one group. A bond is a group, no matter double bond, single bond, or triple bond. That's first rule. Number 2, a lone pair is one group. What's a lone pair? Non-bonding is our group. If you have 2 pairs, 2 groups, 3 pairs, 3 groups. Only these 2 rules. Again, on the central atom, guys, you look at the central atom. If you see a double bond, one group. If you see a single bond, another group. If you see a triple bond, another group. Any type of bond, as long as it's a covalent bond, it counts as one group. Group means what? They're electrons together. No matter it's a double or triple bond, the electrons are together. Number 2 is a pair of non-bonding or a pair of lone pair, one group. 2 lone pairs, 2 groups. 3 pairs of lone pairs, 3 groups. So with that, I will ask a few of you to tell me the following 4 structures. I draw the structure ready for you. Tell me what is the central atom and how many groups do you see based on these 2 rules? I'll ask a few of you. First question goes to Sophia. What's the central atom in the first structure and how many groups on it? Sophia, are you here?
Yes, I'm here. 1 second.
Okay. What is this central atom and how many groups on it?
I don't know.
Olivia?
I don't know.
Oh, you don't know? Anybody else? Anybody knows? What's the central atom?
Carbon.
Carbon. Very good. How many groups on carbon? How many electron groups on carbon?
3.
3 electron groups. Very good. A double bond and what? 2 single bond. So 3 groups of electrons. Okay? 3 groups. Next, water. What's the central atom, guys? We run out of time, so we'll do it together. What is central atom for water?
Oxygen.
Oxygen. How many groups?
2.
Think about it. Not 2. We said a bond is one group. A lone pair is also a group. How many bonds do we have?
2.
2 bonds. How many lone pairs?
2.
2 pairs. So 2 pairs and 2 bonds. How many groups?
4.
4 groups. Next, third molecule. What's the central atom?
Carbon.
Carbon. How many groups?
4.
4 groups. Very good. The last molecule. What's the central atom?
Phosphorus.
Phosphorus. How many groups?
5.
5. Good. Okay. So we'll stop here, guys. Again, next time, Thursday, we will, based on the number of groups, tell people what is the geometry of a molecule. Based on what? Based on this group, we'll do what? We'll try to get away from each other as much as possible. Why? Because they repels each other. This theory is called what? Repulsion. Repulsion means what? These electron groups, no matter how many they are, they want to be separated as much as possible. And then from that separation, we can determine the geometry of a molecule. And again, everything starts with a correct Lewis structure. You can see that without Lewis structure, you cannot even move forward on the shape, on the geometry of molecule. All right, that is all for today. Any questions, guys? Keep. Any questions?
I'm good.
I have a quick
Thank you.
question.
Yes.
Just a quick one. The lone bond or the lone pair, it only applies to the center atom, right? Like if
Correct. Correct.
First
When
oxygen.
we determine the shape, the geometry, we only look at the central atom.
okay.
Yes. Yes. Like I give you guys the example. Think about what do we shape? Flower. The shape of a flower not determined by how many petals, it's determined by the central. Then we look at how many petals around it. The same idea. Okay. No more for questions. We'll end it for today. Tomorrow recitation, we will review chapter 4 a little bit, give you a few practice more. Then your quiz will be on chapter 4 only tomorrow. Still 1 o'clock. Okay. See you guys tomorrow. Thank you all.
Thank
Goodbye.
you.
Bye.
Bye.
Thank you.
Thank you.